So you might have noticed that it was quite tedious to write all of these down, and you can see that it starts to just repeat itself and you're just adding one more electron. So you're wondering, is there a shorthand way to do this, like a shortcut, so we don't have to write everything down? Yes, there is. So this will be your lecture on other notations or other ways of writing electron configuration. The first one is called shorthand notation, or a shortcut, or sometimes we use noble gas configuration, and I'll tell you why in a minute. For this, we use the noble gas above the element and we put it in brackets. Okay, so looking at this, I'm going to go ahead and circle the noble gases first. So helium is a noble gas. Okay, neon is a noble gas. And so is argon. Okay, I believe those are the only noble gases here. Let's see. Yes. Okay, the reason we use a noble gas configuration is because the noble gas is very stable. And so, for example, sodium right here has the same as the noble gas here with a 3s1 extra electron. And as you know, or you will learn later, that this extra electron is going to leave and react, okay? So all of these will react until their electron configuration is close to or similar to the electron configuration as neon, okay? It doesn't turn into neon, it's just it has the same electron arrangements as neon. It's still sodium because it has this 11 protons. So we're not touching the nucleus. So the shorthand notation looks like this. So if I wanted to write the shorthand for sodium, I would write sodium. Number 11 has 11 electrons. The shorthand configuration would be, I choose the noble gas above it, neon. So the same electron configuration as neon plus 3s1. Okay. So let's do another example. Let's do magnesium. Magnesium would be the same configuration as, so magnesium is number 12. The noble gas above it is neon. And plus a 3s2. So this is the shorthand configuration for magnesium. Okay, let's try scandium. Let's see, right here. So scandium has 21 electrons. The noble gas above it, okay, I'm not going to use neon because the one directly above it is argon. So if I use neon, I would have to write more. So I will use argon. So write argon in brackets. And then, so argon is, let's see, stops at 3p6. So then all I have to do is write 4s2 and 3d1. Okay, and that's it. Why don't you try boron? Boron is number 5. Pause the video and do that one. Okay, so for boron, the noble gas is helium, which is not very much help. So this is, instead of writing 1s2, I would write helium. And then it would be, the leftover would be 2s2, 2p1. The next notation I'm going to show you is called orbital diagrams. So as you can see, it's showing the orbitals, and it's a diagram or a picture or a notation. A notation means a different way of writing. So in this notation, I show orbitals as squares and electrons as arrows. So for example, the orbital diagram for hydrogen 1 is, the configuration for hydrogen 1 is 1s1, right? So the orbital diagram is a square and an arrow pointing up for that one electron. Okay, so let's do another one. The orbital diagram for helium with 2 electrons would be, helium was 1s2, so this is the 1s. I don't put the 1s2 because I'm just labeling this square as the 1s orbital. And there are 2 electrons, so you go 1 and 2. Okay, you can see the squares are the orbitals and the electrons are arrows. Okay, let's try the next one. Let's do lithium-3. Okay, lithium, as you can see over here, is 1s2, 1s2, and 2s1. So you're going to draw 2 squares. So you're going to do a square for the 1s and a square for the 2s. Okay, so I'm going to do a square for the 1s and a square for the 2s. And I have 2 electrons here and only 1 here. The squares are not attached because they're not of the same energy. 1s is closer to the nucleus, it is lower in energy and more stable. 2s is farther away, therefore the squares are not attached. Okay, so let's try the next one. Would be Beryllium-4 Electrons. So it would be 1s, 2s. So it would have 2 electrons here, 1, 2, and 1, 2. Okay, so the next one is going to be boron. So boron has 5 electrons. So boron, it says right here, is 1s2, a box for that, 2s2, a box for that. For the P, you're going to draw 3 squares, which corresponds to 3 orbitals in the P sublevel, even though only one of them will be filled up. So it would look like this. A square for the 1s, a square for the 2s, and remember the square is the orbital, and 3 orbitals, 3 squares in the 2p sublevel. 5 electrons, so you would draw 1, 2, 3, 4, and then a 5. Okay, again, the P is and the S squares are not attached. They're different in energy. Okay, the 2s is a little bit closer to the nucleus. The 2p is a little bit further away because of repulsions. Okay, so let's try. Why don't you try the next one? Pause the video. Okay, so the next one is, after boron, it's carbon and 6 electrons. So it has 6 electrons, would be 1s2, 2s2, 2p2. Okay, so it'll be a 1s, a 2s, and 2p. Remember, draw all the squares even though you're not filling them all up. So it would be 2 electrons here. Oops, 2 electrons here. Okay, for this one, you're going to fill in 1 electron, and the next electron, because of repulsion, will go into a different orbital because they repel each other. And this is more stable when they're farther apart from each other. Okay, so this is called Hund's rule. And Hund's rule states that when you're filling electrons, put them in different orbitals before you pair them up. Okay, so why don't you pause the video and do the next one? You can guess. Would be carbon. What's next is nitrogen, then oxygen, 7, and then oxygen is 8. Go ahead and please pause the video. Okay, so it is nitrogen is 1s, 2s, 2p. Okay, so it is 1, 2, 3, 4, 5, 6, 7. Okay, and then for the oxygen, you can, for the 8th electron, one S, 2s, 2p. You write 1, 2, 1, 2. This is going to be the 4th electron. This is the 5th. the 6th, the 7th, and the 8th electron is right here. And that's how it gets filled up. And then you just keep going.